So hello everyone. I'm very happy to introduce Konstantin, which is known to most of the colleagues in the round. So in short introduction probably is rather for the video stream purpose. Konstantin is a PhD student in computer science at the University of Warwick and the New York University. And he holds a bachelor degree in economics from the University of Freiburg. And he has a master's degree in transportation from the Imperial College and the University College London. And his research focus is on representation of spatial phenomena in machine learning methods. And I'm very glad that Konstantin actually was our first Beyond Fellow in the Future Lab and who successfully basically spent 6 months with us. And I have heard a lot of interesting interactions with Konstantin from the lab members. And today I'm very excited to hear what he has to tell from his title, Beyond Fellowship Retrospective, Geospatial Machine Learning for Earth Observation and Climate Modeling. I suppose it will be a very interesting talk. Yeah, Konstantin, the floor is yours.
Thank you very much for the kind words and introduction. Yeah, welcome everyone, and thanks for showing up so early in the morning for attending my talk, where I go a bit all around the place, but I mostly want to focus on my Beyond Fellowship. I'm going to present on a couple of projects I did there, but kind of frame it in the bigger scope of my PhD on geospatial machine learning. So yeah, let's get into it. See if I can move forward. Yeah, there we go. Yeah, so what do I mean when I talk about geospatial machine learning? It's a very broad term, but I will talk about it in a bit more of a narrow sense today. So first of all, I'm going to talk about neural networks. So I'm going to talk about geospatial machine learning with neural networks. And then the second bit is that I'm going to talk about how to integrate the domain expertise that we have stemming from the field of GIS or remote sensing about the very particular characteristics of the data we work with, integrating that domain expertise into neural networks using spatially explicit embeddings. So this is kind of a bit of a more narrow focus. There's of course other avenues for geospatial machine learning, but this is what I'm going to focus on in this talk and also in my PhD thesis. Yeah, so what do I mean when I talk about geospatial embeddings? So I'm not going to go really formal in this presentation, but just for the intuition, what I mean is that I mean with geospatial embedding, I mean somewhat a function that has a set of hyperparameters, lambda, and potential other parameters, theta. And this function maps some input x, which is a spatial input with coordinates c. So that is geospatial coordinates, latitude, longitude, in a geospace. So it could also have altitude, right? So it could be 3-dimensional space, could be 2-dimensional space, and it might also be indexed over time t. So we might also have a geospatial data, but the geographic reference, that is the important one for my interest at least. And yeah, so this function maps that spatial or spatio-temporal input x towards some embedding in space as EMB. And the embedding space can be anything, right? So the embedding space can be the same as the geospace. It can be same as the spatio-temporal space, or it can be some latent space. So embedding in that sense is completely flexible as to the functional form. So with that kind of little formalization out of the way, I'm gonna focus on 2 types of embeddings broadly. Indulge me here because like the definition is not really perfect, and I'm still thinking about that. But you know, I'm also looking forward to hear thoughts on that, because this kind of formulation is what I have in mind for my thesis, but I'm not entirely sure yet if that is like kind of the correct way to formalize it. But basically, we're going to talk about non-parametric and parametric embeddings today. And the difference between them, as I define it at least, is that non-parametric embeddings in my book are non-parametric in the sense that they might have potential hyperparameters, but those are set globally and are static, and the amount of the amount of hyperparameters is also static and just like globally defined for any function that maps x to the embedding space. And parametric embeddings I'm going to talk about are parametric in the sense that the number of parameters grows with the input size. So if x becomes bigger, so if the spatial dimensionality increases, or the number of time steps increases, or just the coordinate c as spatial units. So if you have more spatial units or more time steps, the number of parameters theta should also increase. And of course, the simple example of that kind of embedding would be any neural network that is fully connected, for instance, where the amount of parameters in the neural net, of course, increases if the input is bigger. So that is what I mean with parametric and non-parametric embedding. This is not a definite definition. There are some overlapping areas and some things that are a bit more vague, but for now, let's go for that definition. And I think, at least for the purpose of this presentation, it should serve us well. Right, so let's get right into it. And we start with non-parametric spatial embeddings. So not spatio-temporal, I'll come to that, so just spatial. So let's talk about how traditionally spatial coordinates are encoded in machine learning research. So of course, there's machine learning methods that are good at modeling spatial coordinates. Most famously, probably Gaussian processes used in geography as kriging often, which are of course a kernel method and have like a good intuition for working with Euclidean distance and measuring distance between coordinates and kind of building an autoregressive model. But not all machine learning methods are obviously able to work with coordinates. A simple linear regression model is not able to really capture the relationships between nearby points and more distant points. And so there is a long tradition of devising techniques for integrating spatial coordinates into these models that don't have an intuition for space. Think about linear model, random forest, but also just fully connected linear neural networks. And one very simple traditional way of integrating that is a one-hot encoding, where basically you split your whole observational area into these kind of small grids. And when a point falls into a certain grid cell, it will be activated through one-hot encoding by a value of 1, and all other cells will be 0 in that for that particular observation. And that's kind of lets you plug your coordinates into any classifier or downstream application. Another very simple way of doing that is a nearest neighbor embedding, where you so this is basically what's done in a spatial lag model. So you have one observation, you draw a radius around this observation and take the observations that are nearby and compute some sort of spatial lag, for instance. So kind of the average of the nearby values and feed that into your downstream application. So these are kind of very traditional ways. Now, in the geographic information sciences, obviously there's lots more intuitions for all sorts of spatial phenomena and more complex embeddings. So these are just 3 that I've looked at a lot, and some of you might know, and also like this. So these I've already talked about a bit in my last presentation. The first one on the top left is the Moran's eye, which is just a measure of local spatial autocorrelation. So how similar are nearby observations, and this is a great measure for detecting spatial heterogeneous clusters, but also for spatial change points. Basically compares the values of each observation to its immediate surroundings and the deviance from the mean of all observations. The LOSH, which is local spatial heteroscedasticity, expands that idea but looks at not the difference between values and means, but between variance and global mean variance. And then the LSD metric, which I guess the latest of these from 2018, looks at the difference between local variances rather than the deviance between local and global variance, between point variance and local variance, I guess. Yeah, so as you can see, there's already, these capture a much more intricate patterns when compared to this like simple one-hot encoding, for instance. And I really like that figure from the LSD paper by René Westerholt, who's at TU Dortmund. So check out this research, really interesting research. Basically, I think this figure shows well that kind of these patterns catch very different, these embeddings catch very different patterns, and more globally and more locally distributed patterns. And yeah, so basically there's no one embedding fits all. They're kind of specialized to different tasks. Yeah. Now let's move from GIS to computer vision, because the computer vision community actually has lots of spatial embeddings that, while they're probably usually not referred to as that, they're actually very relevant to what we're doing in remote sensing, because of course we're also doing lots of image processing and image computing. So what we have here is two very common transformations in computer vision. So one is a depth estimation, which is a very common prediction task in computer vision. Of course, the depth estimation measures the distance between each pixel and the camera. And usually that's kind of computed with sensors, but there is a functional approximation that is non-parametric actually, so you can actually just compute that as an approximate rather simply. Another non-parametric spatial embedding computer vision is canny edge detection, for instance, which, you know, for an image gives you the most poignant edges. Now, okay, yeah, so we're moving on to non-parametric spatio-temporal embeddings. I've also one from computer vision, one from GIS here. So from computer vision, very common embedding is optical flow, which again can be sensed much more complexly, but there's also functional approximations for that. So optical flow is just a difference in motion between two time steps of a video. So yeah, there's simple functional approximations for that. There is, of course, also more complex ones. So optical flow can also be a parametric embedding and can be predicted with a neural net. That's actually also a very common task in video vision. And then on the right, we have a also rather recent measure from the GIS community in measuring spatio-temporal autocorrelation. So that is a basically similar idea to the Moran's eye, but aggregated over time. So also lots of work in that area. And this is kind of the first work in progress that I'm working on. So this is together with colleagues from NYU and ETH. We're trying to develop a novel measure of spatial autocorrelation over time. So this one here is on the right side is a static one, and we want to make it dynamic. So this one is not measured over time steps, but the output of this embedding is just the spatial dimensions of the input. And the new embedding that we compute is basically it's the Moran's eye, but we change this little z value, which is the difference between an observation and the global mean. As you can see on the top here, where it says standard Moran's eye. So we changed that approach to use the spatio-temporal expectation here. The spatio-temporal expectation is an idea from spatio-temporal scan statistics, which are very common in epidemiology and kind of the modeling of self-exciting split point processes, which are, for instance, very important for COVID modeling, of course. Yeah, and so the idea of a spatio-temporal expectation is that you assume space-time independence. So you assume that if there was no spatial dependence of the data and there was no spatial dependence of the data, what would you assume at a given time step based on the previous time steps, the value at a point to be? And this is given as this formula here, and then we can plug this into the Moran's eye and get a new statistic. I think, yeah, the video is moving. So we just computed that kind of how that looks for a log Gaussian Cox process. So that's a standard synthetic point process, which can be used for modeling all sorts of diseases, for instance. So you have the Marnes eye in the middle, and you see it's kind of a much more localized effect if you compute that statically each time step, and our new version is a bit more sensitive to these kind of patterns. So you see that it moves much more. Yeah, so this is a new work in progress. Let's now move on to the parametric embedding. So parametric, again, when I say parametric, I mostly mean neural networks. So this is well, yeah, one of my favorite papers of the last years, because it's a kind of a geo paper that actually made it in a big machine learning conference into ICLR. So Spatial from 2019, where the authors propose a really cool sinusoidal mapping of spatial coordinates that is inspired actually by neuroscience. And then, so they have a sinusoidal embedding of spatial coordinates followed by a little neural network. And when they show that this way of encoding coordinates is really able to learn all sorts of meaningful semantic embeddings. Yeah, so I really recommend you check out that paper. There's also a more applied, I guess, embedding, so more focused on real-world applications. So this is a very recent paper from IEEE Transactions on Multimedia, GPS to back. So this is basically the authors with that paper want to create a global pre-trained model that kind of has features for every GPS coordinate that you might feed in. And these kind of global embeddings are learned through the coordinates and all sorts of semantic information, right? So they have check-in data from Foursquare, they have tweets, they have Flickr images, and they learn a combined representation of each point split into UTM zones. So they actually do a bit of divide and conquer. They train one neural net for each UTM zone, I think, and have, so basically if you want to access a model for Germany, then you need to kind of get the model that has been trained on that UTM zone. So this is kind of a very cool end-to-end solution for integrating like geographic knowledge together with the semantic information at that location. Moving again to computer vision, and now it becomes a bit more abstract, but basically all sorts of self-supervised learning methods are also often related to embeddings, right? So this is a very recent approach in contrastive learning, where basically also you have neural networks that take in all sorts of spatial augmentations of the input and try to learn a robust representation. In my definition, this is also nothing but a spatio-temporal embedding. I think in general, it's kind of important here to emphasize the connection between what I understand as parametric embeddings and representation learning and self-supervised learning in general. All right, so having talked about a couple of embeddings, let me move on to the next step, which is how to integrate the embeddings into neural networks. So again, to recap, I guess, with these embeddings, I seek to capture all sorts of interesting spatial phenomena that neural networks themselves might not be able to capture or might not be able to work with so well. But since we have domain expertise from our field, we know that these effects exist, and therefore we can capture them in embeddings and feed them into neural networks. I will talk about two ways of doing that. The first thing is a multitask or auxiliary task learning, and the second one is just simply adding them as additional features. So this is also a bit of repetition from my last talk, but basically the idea of auxiliary task learning is a simple multitask learning problem where you seek to predict two outcomes with one input. You have some shared layers that where you feed the input through, and then the top layers of your problem are going to be task specific. Yeah, so auxiliary task learning is the same idea, only that you're just interested in the outcome of one task, let's say task A. You're not interested in task B, but research has shown that actually adding auxiliary tasks makes a learner more robust and might actually improve performance. So this is one way to integrate these spatial and spatio-temporal embeddings. And this paper I talked about the last time is one of my papers where we basically have models predict the Moran's eye embedding of a spatial data set in parallel to the actual output we want to predict. And we show that somewhat kind of robustly improves performance on generative and predictive modeling problems, so in very different settings. Now to some work in progress of mine, focus on additional features. So the task that I'm looking at here is the question of whether we can improve spatial regression with graph neural networks if we include some of our parametric spatial embeddings. So a traditional graph, a convolutional network for a spatial regression problem would look like this. You have some geodata. At each training step, you randomly sample a batch of data points, spatial points that come. So the points are P with X are the node features, C are the coordinates of each node, and then Y is an outcome at each node. So you sample the data points, you construct a KNN graph connecting each node to the nearest neighbors, and then you feed the graph into a graph convolutional network with the node features to predict the outcome Y, and that gets you your loss. So that's kind of the traditional approach of graph convolutional networks for spatial regression. Now, what I've been doing in this project is I've tried to see if learning a meaningful spatial embedding at the same time actually helps improve the model. So the beginning of the pipeline is the same. We again randomly sample a batch of data points. We again build a KNN graph and again have our graph convolutional network predict the outcome. However, in parallel to the graph convolutional network, we also have a spatial embedding, a parametric embedding. In this case, I use a space-to-vec. Have a space-to-vec encode the coordinates of each batch, and then feed them through a linear decoder that also seeks to predict our outcome. So we have kind of a fusion, if you will, as from one data set. So it's not really fusion. It's a multimodal approach, basically. So we have our space-to-vec model try to predict the outcome, and we have our graph convolutional network predict the outcome. In the end, we combine the inputs and we compute the loss. And yeah, so it seems that this shows some promise for actually improving performance. So it seems that learning a meaningful spatial embedding of your coordinate space at the same time as predicting the outcome actually is meaningful for improving performance. All right. So having talked about kind of my work on geospatial machine learning and embeddings, now I want to move into some projects that I'm working on currently, and with those I want to highlight a bit on why I feel that this is such an interesting field and so needed. Yeah, so why do we need geospatial machine learning? Yeah, the first reason I have lined out here is because we can help neural networks get better with the sort of particular data that we're using in remote sensing and geography, and especially with the kind of very intricate structures that we have in for instance, geophysical data and all sorts of all sorts of other geodata. So, for example, if you think about the climate data, it's often very physics driven, right? So you have, for instance, turbulent flows and also self-exciting processes in climate data. And neural networks don't necessarily have a good intuition of learning those, but this is all changing currently with this kind of big paradigm shift towards physics-informed deep learning. So if you follow the big machine learning conference, you'll see that over the last year or two, there's been much more research on physics-informed deep learning and kind of integrating constraints of the physical world and also prior knowledge into neural networks. So this is a project I've worked on with Sudipan, who I think is here, and Matthias as well. So this is a paper that was presented at ICLAIR workshop on oceans and climate modeling. And basically, the idea here is to use a GAN to do extreme weather simulations. So we have think about the pipeline as follows. We have a mask of extreme weather events, which is the first row in the bottom figure. So basically, that's a mask of all sorts of extreme weather events, like a tropical depression, hurricane. Can be anything, and it's a spatio-temporal mask, right? So for each pixel, we have an encoding. Is that a part of an extreme event or not? And then we have that over time. So the weather events, of course, move. So our goal is, given that extreme event mask, can we model realistic weather and climate data that corresponds to those extreme events? And so what we use for that is a novel spatio-temporal GAN. First, we built a mask encoder that encodes all that spatio-temporal extreme event information and feeds it into the GAN generator and discriminator, and then uses that encoded information to generate these patterns. And this is work in progress, so we haven't trained the big models yet on that, since we need to work on the architecture a bit. But the first results were somewhat promising, and so I'm excited to continue to work on that project. And the potential application of that is, of course, running large-scale simulations of extreme weather events, which might have all sorts of applications to for instance, disaster prevention. Of course, it will be interesting to see how our approach using deep learning compares to the kind of traditional approaches that are used for these sort of problems. There aren't so many. Most of the work on this is on forecasting, which we're not exactly doing. We're doing more like simulation, but yeah. So I'm excited to continue to work on that. The second little project I want to talk about today is so the second reason why I want to talk about geospatial machine learning is because current methods in machine learning, computer vision, are often focused on abstract tasks and data, as you all know, data sets that are not necessarily representative of the real world. And we observe that they often struggle when we transfer them to the real world. So one example, the example I want to bring here is point clouds, right? So if you look at the literature on point cloud segmentation or point cloud generation, as in this case, it's often done on data sets such as ShapeNet. So ShapeNet, if you don't know that data set, is a data set that has point clouds of objects, right? So chairs or airplanes. And this is, of course, somewhat abstract data set, and it's still, of course, very useful to devise new methods and test out things. But what we observed is that it's really difficult to transfer that to the real world. And we did that when we tried to generate real world point patterns. So that is, for instance, on the top of this figure, you see 311 calls in New York, and on the bottom, you see a Beijing taxi trajectory. So these are just coordinates in space. And our task in this project is to generate them realistically using GANs as well, and then also privatize them. So that so privatizing means that you train the model with differential privacy, so that any data set you will publish based on your GAN is then also differentially private, so kind of protects the privacy of whoever created the input point in the first place. For example, if you go to safari in many African countries right now, at the entrance of the national parks, you will see pictures that will ask you to turn off geotagging for your photos. That is because poachers can use geotagged images to try and poach animals that they see are at a certain location because you post a photo of those on social media. Now, what we aim to do is to create data sets that still realistically represent the actual data, but that are differentially private, so that protect the underlying data, the underlying individuals, but are good representations of the actual data. Yeah, and so we found a method to do that by improving over existing GANs. So we tried a couple of different GANs that are optimized on these kind of abstract shapes. And we saw them all fail when applied to this real world task. So we kind of had to devise a completely new method. This is how it looks basically. It's using all current modules. So the deep learning here is not super novel. The architecture is quite different, but it's not like a huge change. Basically, we use large point nets to capture these kind of intricate patterns and generate new points. And then to create differential privacy, we apply a very simple trick, which is so that requires a bit of knowledge about GAN. So a GAN learns by showing the discriminator real and generated data and have the discriminator predict whether the data that it sees is real or fake. And then the generator tries to generate data that is as realistic as possible and tries to fool the discriminator. And then the GAN learns by having a game between discriminator and generator where they each try to get better. And ideally, if that training goes well, you'll end up with quite realistic generator that can generate the data. And so what we do to achieve privacy is just to randomly flip the labels that are given to the discriminator, the real and fake labels. And that's provably, so you can prove that this creates a private generator that creates local differentially private data. Yeah, and so this is how the data looks like. So this 4 different data sets of real-world geospatial patterns. So the top row is the city of Porto, it's also taxi data. The second row is Beijing. Then we have New York, 301 calls, and the last one is actually 3D data sets. I just don't have the 3D plots here, but that's the 3D roads data set. Yeah, and so on the second column, you can see kind of the best performing current existing method, which is a method for these kind of little abstract shapes, RGAN. And as you can see, it's not able to resolve the structures at all, whereas our method is quite a lot better. Yeah, and that brings me to my last project. So why geospatial machine learning? Because it can actually be very helpful at monitoring our planet. The project I want to talk about here is kind of the most recent one. So this is a master's thesis by a student that I'm supervising, who does her thesis with Shaoshang and also supervised by a couple of colleagues at ETH and MIT. And the project here is forest observation, right? So forests are integral for limiting and mitigating climate change. And as you probably all know, if you took a plane in the last 5 years, carbon offsets are becoming increasingly popular, and they're a way of financing forests, right? So you can do a carbon offset of your flight where you give a little donation that is put into carbon offset of the carbon footprint of your flight. However, the certification of these carbon offset programs is expensive and often intransparent. So what this student, Giri, did is, so she, with the help of a couple of other projects, created a benchmark data set from 6 agroforestry sites that is very detailed data, and it has the AGB, that stands for above ground biomass from these sites. Yeah, so the above ground biomass usually is computed using something called allometric equations. So that is basically for each species of tree or like larger plant, there exists an equation that gives you the above ground biomass of that plant, given the diameter and the kind of the height of the tree. So these equations you see on the bottom right corner. And the interesting thing about AGB estimation is that it's actually done a lot currently, right? So there's a whole global coverage data set for the whole world by Global Forest Watch, for instance. And these estimations are usually done using satellite data. However, what our student found out using these very granular, very local and precise data sets is that the current satellite-based estimates significantly overestimate the above ground biomass by on average a factor of 10, but as you can see in this table, for some sites the overestimation was as high as 56 times the true AGB. So it seems there's lots of work to do, and so this question is so interesting that we actually got a spotlight talk at the climate change workshop at ICML, which is of course a very big success for a student. We're very proud of her, but it also kind of highlights how important that problem is. And of course we believe that that machine learning can help solve that overestimation problem by training on very precise data and then being able to generalize to the whole world. So that is one thing, machine learning. The other thing is to use better data, because it seems that satellite data, at least at the resolutions that we have, is not good enough. So what we actually have for a couple of these sites is we have drone imagery, so much more granular data, and so we hope to use that data to create better models of above ground biomass, and then kind of maybe generalize our work and kind of see if we can get better predictions of above ground biomass, again supporting processes like carbon estimates. All right, I think these were all of my points. So it was a bit all around the place, but I'm happy to take questions and chat about all of the different topics I talked about today. Yeah, thanks again to the AI4EO Lab and Professor Xu for having me at the AI4EO Lab. It was a great pleasure, and I will, of course, continue to collaborate, and very much looking forward to that. Yeah, thank you very much for coming today.
Thank you, Konstantin, just in time. Thank you for sharing this review about your achievements and current work, very interesting. We also thank you for your contributions in the lab. And
thank you.
We hope this has been as well enjoyable for you. Now we turn to any questions that the audience may have. Just if you have any question, please feel free to turn your microphone on, and yes, take this chance, these minutes to ask Konstantin before he left our lab.
Maybe I have one question to your last slide, the slide before, Konstantin. This is a dramatic statement, I would say, that that above ground biomass has been overestimated by a factor of 10 in the past. On the other hand, the numbers I see here seem to me very unrealistic. I mean, this is kilogram per hectare, and it's only 19 kilograms per hectare. I mean, if there is a single tree on a hectare, then it has already a ton or something like this of weight. Are the units correct here?
Yeah, so the problem with this is that these are very specific sites. So we don't claim that this is like a global estimate is off by a factor of 10. So the problem with these sites is that these are very specific species of plants, right? And the problem with current kind of more global estimates is that they don't really distinguish between the species. And so for instance, for these sites, we have lots of banana and cocoa trees, and they have a very different above ground biomass, or like the way to calculate that is much different than for other plants. And so one thing that we believe is the reason for those sites being so off is that the way the calculation is done is just wrong. So that we have to dig a bit more into that, but kind of what we assume is that there is parts of the world as defined by the ecosystem there that are just significantly overestimated rather than overall.
Yeah, okay, but I mean, in usual areas in forests, they usually have hundreds of tons per hectare, so they are a factor of 1,000 denser. So if this very sparse vegetation is underestimated or overestimated, does it then really play an important role in the whole budget?
Yes. So I don't think we can make that claim yet. I think what this kind of project raises, since these are also very, very small observation areas, right? So if I go back to that slide, you see we look at 4,600 trees, so that's nothing. But the little snapshots we took were very off, and these happen to be in countries that are that have these sort of species that are apparently not ideally calculated. So I would agree for now that this probably doesn't make huge of a difference now. We shouldn't make that claim, and I don't think we do in the paper. But I think more importantly, we kind of raised the question, and you know, what it motivated us to do is to kind of dig a bit deeper and see if we can find this pattern more generally. And if not, then what is the reason that we can observe this at our spots, but maybe not globally? But for now, I would agree with you that this is not a huge issue in the budget for now.
Thank you.
Any further question or comment?
I would like to continue, not this topic, but rather the GAN-based, you know, geospatial data. Privacy is, of course, an important issue to be considered. We are facing the same situation with the social media data, right? So
yeah.
Tweets since middle 2019, there is also basically kind of noise in the geolocation. Which makes it very difficult, for example, to assign tweets to buildings and so on. In remote sensing, we are, however, seeing this kind of data as a very precious, unconventional geodata source. But now, what is it's more a philosophical question. What is a good balance? So, I mean, with the current Twitter geolocation policy, for example, this of course made what could have been possible to a larger degree now less attractive. And on the other hand, ethics and everything. So what is your view on this topic in general? So it's not directly geospatial machine learning, but I guess it's important.
Yeah, it's not directly geospatial, but I think this project, I wanted to include it because it highlights how existing methods can fail when they're transferred to the much more noisy and complex and convoluted real data, rather than these very clean and sterile toy settings, basically, that we create in machine learning. So my opinion is that we need to change that, right? I see why we have very simple and kind of basic data sets to first test our models. That's very important for kind of really fundamental machine learning research. But I don't think it will be a big help of us if we all overfit all our models on ImageNet, so to say, right? And I think there is a big lack of benchmark data sets that are actually representative of how the real world works, especially when it comes to geospatial problems. I know that you had a challenge at CVPR, so I see that there's more of these kind of data sets coming now, and people are acknowledging more that you know, current benchmarks are not really ideal, and you always get those problems when transferring stuff to the real world. So I'm happy to see that. Yeah, but I don't know. It's difficult. I guess it's a trade-off.
Yeah. Anyway, I'm not expecting any, let's say, answer to the question. Rather, just want to hear your opinion.
Yeah. Yeah.
Yeah. Okay. Am I allowed to ask another question, Diana?
Yes, please. We still have time.
Yeah, so I see that you now also works with climate data. We also had a discussion before, and you also have been working with graph convolutional neural networks. You know, for modeling this kind of complicated processes, we usually have a lot of geospatial variables. I see great potential to use graph structure somehow to model relationship of these parameters to a certain processes. And my question to you is, what are the potential challenges you see more or less in this particular setting?
Yeah, so I think the biggest, so the biggest challenge I think of graph nets for geospatial data is finding the right ways to construct your graphs. So of course, in the real world, if we construct a spatial graph between coordinates, the standard way to do that would be just to use Euclidean distance between points. That's often not the distance that is actually true, right? If we are lucky enough to have our data laid out on a map that is, you know, publicly available, like OpenStreetMap, we can try and get the road distance between points. But I think this is kind of thinking about distances is very, very crucial for kind of applying graph neural nets in the real world. So finding good ways of actually measuring distance between points, because I mean the famous examples are always, you know, somewhat segregated cities in the US, where you have a really rich and a really poor neighborhood that are very close together but separated by a big highway or so. So a graph like a Euclidean distance graph neural net might see those as neighbors because they're like spatially close. But if you look at, for instance, a street network, they're kind of separated by a big highway and like a long way apart. So I think thinking about distance is crucial, one of the biggest challenges, I would say. Otherwise, maybe the black box nature. I'm really excited about graph neural nets because they're very powerful and they scale really well, and they allow us to model very flexibly. But of course, with the kind of real world problems we look at, we usually want inference, and graph neural nets, as any neural nets, are of course black boxes and not necessarily the best way to get inference. So I think, as happy as I am for the kind of push on this kind of geometric deep learning and applying that to spatial problems, I hope there's also always people who kind of call for caution of using these methods, especially when applied to social data and socioeconomic problems, right? Because that's the kind of problems where we want a lot of inference and we want to understand the processes, maybe causality, and where machine learning can actually do lots of harm because it will, you know, it might lead to some associations that are, you know, that might be true, but that might not in any way represent causal relationships. So these are, I think, maybe my top two worries or challenges, and I hope that people are working on those.
Yeah, so it's a very interesting insights, but I actually also meant probably multi-scale of the variables, including also the causal relations, because not all these thousands of parameters are contributing basically to the processes. So maybe this kind of question can also be modeled with graph, but I'm not sure.
Yeah, I mean, I think there's some cool work on regularizing graph neural networks. I think especially if you have like huge feature space, that might come in really handy for selecting the ones that actually matter. So yeah, for sure, that's also really interesting field.
Yeah, thank you. So I think I stop from here because there might be other audience who want to ask questions.
Any final question or comment?
Maybe I have one. Hi, very nice talk, very interesting. And I'd like to ask a following up question on what Charles Shang already asked regarding the social media data, because if we look at the Twitter data, we see it is, with respect to privacy on different levels. You can have it on a let's say on a place level, you know where the restaurant is, but you can go also, some tweets are marked just with a neighborhood they are in or the city they are in. Do you see that, or how we could deal with something like that, to have these kind of different levels of privacy in between?
That's a very interesting question. I think it depends, because the granularity is only one issue, I think, because even if you go to let's say like a higher level, like let's say you don't want to privatize a specific location like point coordinates, but you just want to privatize on a, I don't know, block level, like a block of houses. If that area happens to be like very sparsely populated by points, you will still have the same privacy issues as you would have on the point location. On the other hand, if you on the block level have a lot of observations in that block, you don't have those privacy issues anymore that you would have on the local level. So I think the spatial resolution, so to say, is just one problem. The other problem is if you're kind of in a very densely populated area or not. I think though that there are probably ways of doing that that would involve plugging in your privacy mechanisms at different resolutions, but kind of maybe randomly mixing them. That's one thing that comes to my mind first, right? So randomly privatizing at different resolutions, maybe that will lead to something that can solve that. But I think realistically, the answer is much more depressing, which is that I guess you have to find a solution depending on what application you have, right? And depending on the situation you're in. Like, I think the most realistic option is to actually have it very ad hoc, which of course is not what we would want, right? We would want to kind of have a generalizable solution. I do not think we're close to that yet, from the research that I know at least.
Yeah, I agree. Thank you very much for your comment.
Okay, so time has run out, unfortunately. So I think we can give this talk as conclude. Thank you very much again, Konstantin. We wish you a lot of success in your future career and in the future challenges you may have.
Thank you.
We also give thanks to our audience. We hope we meet for the next meeting, for the next meetings and talks. And have a nice Friday all.
Thanks for the great questions, everyone. Thank you for having me.
Thank you. Bye-bye.
Bye.
Bye.